Okay, time to start this. I'm sure it will be great. Okay, so happy Thursday, everyone. So, how do I even explain this? Okay, so this is not an actual screencast. This is me doing a really stupid challenge because, like, why not? So if you've ever seen my channel, you might have seen this video where, oh god, where I compete in a round using the best font. I don't know how to write wingdings. So yeah, I just did like an entire round using that. It's actually a bit easier than it sounds. You can use like syntax highlighting or whatever, and it helps you a lot. So naturally I tried to do something harder for today. Okay, let me comment this out for a second. So, welcome to the cursed font. So what this font does, as you might see from this preview, is it turns pretty much every non-white space character into an A. I considered doing uppercase A instead, but I thought it was funnier to just have lowercase a for everything. So yeah, this is probably going to be considerably harder because, like, at least with wingdings you can like learn the character names to debug or whatever. Here you have to do something fancier if you want to ever debug, I guess. So yeah, I'm using Sublime and I'm using like a regular terminal to compile. Probably cringe, but whatever. Yeah, this is part of the theme for today. So we're doing Codeforces Round 721. Like, even with this stupid restriction, I'm actually going to try to do as well as possible. I'll try to do some commentary if I can, but first of all, I haven't tried this ever, and I'm like bad at explaining things. And I'm also like generally bad at talking, if you haven't noticed yet. So this is probably a really terrible video, but feel free to watch it, I guess. Or feel free to not watch it, because I don't think anyone should ever want to watch this. Okay, I think that's the whole preamble. Oh yeah, our BGM for today is here everywhere at the end of time from the caretaker, because it just fit, I guess. So actually, this is already hard. I'm going to try to type my template, which is very simple, gratefully, because this would be extremely impossible otherwise. Also, I don't use like autocomplete or anything, not that it matters a lot for this stupid challenge. Yeah, so this is what you're in for if you actually decide to stay for some reason. Okay, let's see if this compiles. That would be great. Okay, cool, it actually compiles. So presumably I wrote what I wanted to write correctly. Everything else just uses the regular font, so I can see normally in my terminal, and I'll try to... I can also see, like, if I actually submit code, like I can see it in Codeforces, but I'll try not to abuse that too much, because it kind of goes against the spirit of this dumb challenge. So yeah, I might like explain solutions at the end if I still have the will to live somehow. But yep, contest is starting and let's try to do well. Good luck, everyone. Find maximum value of k such that this holds. Okay, why can't we choose just k equals n and it's just 0? Wait, what? Oh, it's the opposite. I see. So I think it's just like the smallest power of 2 minus 1 that is less than n. So this should actually be EC. How large is this? Not too large. What about 1? Like it actually doesn't exist for 1. Or no, wait, it does. It does. So I just have to start at 0. So this is n, this is read n. So let's start at 0, and well, I think times 2 plus 1 is at most n. We times 2 plus 1 and then print that. So let's see if we succeeded in writing something that actually works. Yeah, I think we did. Let's try one. Do we want strictly less? Yeah, like 15, that doesn't actually work. So 2 times x plus 1 less than n. Yeah, so now if we try 1 and 15, 0 and 7, which is what I expect. So I think this is correct. Like, I can prove the solution, but I think the code is correct, I guess. Let's see if it actually looks... Yep. Okay, so I'm not a complete failure. I actually solved one problem. Pretty slowly, but whatever. So apparently C is really easy, so let's try to read that first. The weight is the number of unordered pairs with the same value. Print the sum of the weights of all subsegments. Okay, so I guess we just want to count like what we actually want to count is the number. What am I saying? We want to count like the contribution for each pair. So like 1, 2, 1, 1. This 1, 1 appears in 2 times 1 subsegments. Okay, so we want like product of L times n minus R over all guys of the same size, I think. How do we actually do that? Okay, I think I see how we do that. So we like keep all positions for a certain value in order, and then for each position like compute the prefix sum and then multiply. I think that works like vaguely. Oh god. So right now I'm just reading. No, I don't want this. So this is map int vector int, like positions, I guess. Just pass. Okay, so we should have a map of arrays of positions, and then yes, so this was a really good idea, as you can tell. Okay, I'll stop complaining. Will I stop complaining? Oh. Okay. So this is the size of our current array. I think I already used this name, but hard to actually tell. So I add n minus position, which is vi, and then what I do is sorry about leaving for a second. Okay, I think this is the full code for this problem, but it's very, very likely that I screwed it up. Oh, holy crap, that is loud. Okay, so line 25. Oh, jeez. This was a really good idea, as you can tell. I think this is what I need to modify. No, it's not. Oh, this? What the heck? What is that line? Okay, so this is 18, 19, 20, 21, 22, 23, 24, 25? What? This is 25, I guess. And this was actually what I needed to change. What? What am I doing now? Oh. Yeah, I see. Okay, this is probably still... Well, at least it works unsampled. So I'll just submit it, what the hell. So yeah, as you can see when I actually submit, you can tell that I'm like actually trying to write like decent code, even though I'm not even reading it. It just makes more sense for debugging anyways, I think. Is the queue long or something? Nope. Okay, so that was actually correct. Surprising. How are we doing? I'll look at front standards because it's like easier to go from there. Oh, alright, I'm supposed to show an official to actually see. Okay, we're not doing that terribly so far. Okay, let's just do the hard version because why not? So, define a palindrome, you have a bit string. You can change 0 into 1, and you can reverse for free if it's not a palindrome. And you can't reverse 2 times in a row. Okay. I understand the game now. But how does this ever end in a draw? Oh, okay. So you want to use the second operation as many times as possible. So, like the only thing that should matter is how many zeros you have and whether the string is currently a palindrome. And no, because you also need to like know when it becomes a palindrome. It kind of doesn't seem like draws are ever possible. Okay, how do you do the S's and palindromes subtask? Like Alice can't do anything. Like Alice has to pay. I guess if you have 2 zeros in a palindrome configuration, Alice can't do anything. Like she has to fill one of them, and then you can just reverse. So this is just always print Bob, and I guess we'll just do that because it's stupid easy. Unless there's... No, unless nothing, it just works, I think. Because if you end up with odd lang at the end, then Alice has to... like she has to choose that one anyways, so it doesn't actually matter. Apparently that's wrong for some reason. Like, it's true. Oh wait. If initially the middle character is 0, then Alice can force a draw, unless it's I, 'cause, 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 ' unless it's exactly just the string 0. So okay, it's less of a meme than I thought. So if n is odd and the middle character is 0, is it? Yeah, I think that's what happens. Like, I don't think Alice can actually do any better than a draw. And n is at least 3. Then it's a draw and continue. Is it a draw? Oh god. No, Alice actually wins for the... Yeah, it obviously can't be a draw. Duh. Okay, so there's actually... God. Okay, I think it actually works now. So that's the easy version, and the hard version is probably something really dumb. I don't know. Hard to tell. Let's hope I didn't screw up again. No, that's actually correct this time. Okay. So so for the hard version, like what we actually need to identify what the string is like, if it's odd, then we need the middle character. I don't think there's a way around that. Then from the other characters, we want the number of 0, 0 pairs, 0, 1 pairs, and 1, 1 pairs. And that determines everything, I think. Okay. So if the middle character is not a 0, and also if n is even, then can we guarantee something? Like, it feels like we can, but also I don't see it quite. So as long as we have at least one of the 1-0 pairs, the string is not a palindrome, and otherwise it is a palindrome. So that means that if we can get Alice to... Okay, let's say there's at least two 1-0 pairs. Then we can, as Bob, play correctly so that... I think in that case, Bob can't lose, basically, is what I'm saying. Let me think. So if you have 1-0s, you can make it so that you, as Bob, will take the last 1-0. And then after that, you have just a bunch of 0-0 pairs to fill. And then yeah, just Alice will have to waste more. So I think if there's 3 or more 1-0 pairs, we just win, like directly, by just stalling enough. If there's 2 1-0 pairs, then it's trickier. Okay, so we've solved if it's a palindrome, so we assume that there's at least one bad pair. If there's exactly one bad pair, then Alice just has to win, I think, because like she can flip and it stays exactly the same, except Bob now has to move if he wants to. Okay, wait. Okay, I think it's even stronger. If the initial string is not a palindrome, then Bob can't ever win. Bob only wins at palindromes. So it's draw versus everything else now. Yeah, that's a good observation. Do we think draws are possible? I don't think draws are something that can happen. Like, it clearly isn't if there's an odd number of zeros. What if there's an even number of zeros? Oh, I think we entered stage 5 now. Yep, that sure was something. Oh, the middle character is very annoying. Okay, so let's say it's not a palindrome and you have two 1-0 pairs. I think Alice just wins by just like if Bob plays on a 0-0 pair, then Alice just does the same. Like she plays on the opposite of that pair, and then on her turns she just flips the string, so Bob is actually forced to take something, and then that will necessarily just make her win. So if it's not a palindrome, Alice just wins, I think. Except the middle character is extremely annoying and I don't know how to handle it. But she at least draws. So 1-0-0, for example, what happens? So what's annoying about that is it can be the case that Bob just stalls for a turn. He takes 0-0. What am I saying? Okay, so we've solved the problem except in the case where the center is 0. And in that case, I'm not sure what happens. 1-0-0. So Alice wins if she doesn't have to take anything. But I think Bob can prevent that. Yeah. Okay, so let's say you have 3 anti-palindrome pairs and the center. Okay, I think anything with more than one anti-palindrome pair, quote unquote, will give Alice a win because she just wins by the number of pairs anyways, normally. So it doesn't matter that Bob also gets the center. So the last case is we have a single thing that isn't a palindrome, everything else is palindromic, and then what happens? Like obviously Alice won't play there. I have a hunch that that's where the draw actually happens. Like it's always a draw, but I'm not completely sure. Let me play a game against myself. So if it ever becomes a palindrome, yeah, like Bob can just force you to take forever. Yeah, okay, I think if you reverse, then Bob makes it a palindrome, and then he just forces stuff. Does he? Does he? So he grabs one, then you grab the center, and then when he tries to do something else, you reverse. Yep. So you still win in that situation. So something else has to happen. If you start by reversing. So you start by making to call. Then you just lose horribly. If you start by reversing, that happens. Well, no, we haven't analyzed that. This is hard. If you take the center, then B just makes it a draw. And there's nothing you can do about it. So you have to either reverse or take. And if you reverse, then B just defeats you, I think. Well, doesn't defeat you, but oh. If you reverse, so bad. To take down that. While both the center and the other thing are untaken, that's just withdrawing. It's bad. Okay, I think Okay, let's try that. Otherwise, I think I'll just assume that it's always a draw and I screwed up the analysis somehow. Though I kind of doubt that. This is annoying. No. How will you ever stop me from winning in that position? If I reverse, you take the one that makes it a palindrome. If I then take the center, then you just die. Like if you start by doing anything other than making it a palindrome, I think you just lose. Because I have like a 1 point advantage on a string that is not a palindrome, and I never lose on non-palindromes. So you actually have to do that, and then I just screw you. Like, I don't see what the issue is. Is there anything I'm missing? How else could you ever draw? I don't get it. Both of these are draws, as expected. Both of these are victories, as expected. Okay, let's go back. Assume we've correctly analyzed palindromes. Alice can never lose on a non-palindrome, because if she did, like if B had a winning strategy, then either by starting or reversing, she could emulate that winning strategy. Is that true? That might actually be the issue. Is that a correct argument? Yeah, it is. If B's winning strategy doesn't start by reversing, then A just does it. No, wait. Okay, so the issue is when B's winning strategy is reversing, starts by reversing after A's move. With what? Yeah. B has to have a winning strategy that starts by actually making a move, because A can just reverse at the start, and then after that A just copies it, and it's completely fine. Like, reversing doesn't actually change anything. So Alice never loses on non-palindromes. When does she draw? So she obviously doesn't draw in cases where oh wait, I'm so dumb. Okay, this is actually a bit more complicated because this will incorrectly recognize, for example, yeah, this will think this is a win for Alice, but it's not. Okay. Okay, I think this should work now. Yep. Let's run on the sample. Yep. So this should be fine now. We finally finished this impossible problem, I think. Oh, yeah, that was interesting. No, we're actually worse off. Interesting, I guess. Oh. Yeah, I see now. We're just really bad at everything. As expected. Yeah, we just suck. Oh god. Okay, finally. This should actually work. Hopefully. Yeah, this isn't going too well anymore. Oh well. It happens sometimes, particularly when doing really dumb stuff. How many people have solved this? Yeah, a bunch. Well, okay. Could be worse, probably. marginally. Okay, let's go and read the 2 remaining problems. Count the number of pairs. Count the number of paths with max equals something. Okay. Okay, so you have a bunch of ranges. Sorry. We want to split the array into a bunch of ranges to minimize this thing here. Okay, let's ask for clarification. I think this is a stupid question, actually, because we never want to have an empty range. It's better to just have a 1 element range. Okay, yeah, it doesn't actually matter. Okay. So, is this alien's trick or something? Let's think. Okay, I think. No, I don't think. I never think. I'm really wrong. These are weird bounds. I'm guessing we're looking for something NK-ish. Persistence deck tree, maybe? Like to query up to a certain point. Like we can query in some version of no. That shouldn't actually work. Or should it? Very important question. So assuming we do that, we want Okay, can we like go from right to left and keep the cost of a subarray? Like, when we add a new element, we add something to everything after a certain point, and then our updates are like adding something to everything in a suffix, and then our queries are maximum. And then we just like do that 100 times. That sounds like something that works. Sorry, k times. Okay, do I want to do this? I guess I have no choice. Like, am I just going to like stop trying? Okay, let me just make sure that this actually makes a lick of sense. Yeah, I guess it's just what we have to do, and there's really no way around it. So, this is going to be interesting. So, oh my god. Time to code a segment tree with this skin, a lazy segment tree. This is probably not going to end well. This is not how functions work. Sorry that I'm like dumb with saying anything. I'm just trying to focus for a bit. Okay, that is our build. Okay, and then our query. This is actually supposed to be a min segment tree, which means I'm dumb, but that should be a really easy fix. That also means this has to be like infinity instead, where infinity is something big. Okay, so this is really bad. But maybe not super bad. Okay, so this is theoretically actually a segment tree. Incredible. It's probably wrong, but I mean, I tried, okay? Cut me some slack. Okay, we're going to read. Let's see how we're doing. Let's see if this makes any sense at all. Yes, it does. It makes perfect sense, actually. Too much sense, even. Okay. So now we want EP. Okay, let's check that this also makes sense in this case, because why not? Okay, so now we're going to do DP and temps. Oh no, first we're gonna initialize. initialize for infinity, and now we're actually doing stuff. Okay. Now, okay, so there, what we're doing is taking everything in some suffix and adding the new element, which will induce a new cast. And then we want to take the minimum over everything after something. Yeah, I'm very good at explaining things, as you can tell. Don't worry about it. So this is from I to N. And this should be actually most of the solution if I didn't screw up, which I probably did, but we can hope, right? What? Dude, imagine if white spaces were also A. That would be so cursed. So stupidly cursed. Maybe I should do that someday. No, I will never do that. That's a terrible idea. Okay, so the good news is nothing. The bad news is everything. What the hell is this? Oh no. Okay, so actually one thing I just noticed is that I want to initialize this differently. I want this to be infinity instead. Like, that's not going to fix this, not at all, but it's something that I actually want to do to make this actually work. What is happening? This is the tree. It has n elements. So we're going to update the tree to include the previous DP value at position +1. That seems good. Okay, so this is probably what's wrong. Let's print this. and then we update from the next position to and with this difference. Yes, I do mean that. Difference from 6 to 7, 5 to 6, 3 to 5, and 2 to 3. That looks good. Which is actually really bad, because it probably means what's fucked up is our segment tree. Or is it? Does it mean that? Maybe? Give me a second to think. Okay, let's write a debug function for a tree. Yeah, okay, this shouldn't be this. That doesn't even really make sense. Oh wait, I'm adding. Oh, I'm so dumb. Okay. So I think the easiest way is actually to just initialize to 0 initially, which is what I said we shouldn't do, but we should actually do it. Yeah, I'm dumb. I'm really dumb. Okay, so that's actually correct now. That's indeed the minimum. So yeah, I add this. Yeah, the minimum is now 1 over the whole interval, and when I combine the intervals I care about, the minimum is 1. So let's where's the debug? Is it like, yep. Okay, so let's comment this out. Let's see out what the query is actually giving us. Okay, so it's actually giving us the correct values, which is very weird, unless I did something really dumb here, which... please tell me that's not the issue. I'm so dumb if that's the issue. That's the issue. sad. Okay, well, that's just really sad. But whatever, what can we do about it? So after this, we're done. If I'm actually good. All words. Yeah, so this should just be the answer at the end of all those rounds of DP. And I also need to erase this print. Is this fast enough? Probably. Probably not. I don't know. Who actually knows? Where am I printing stuff? Oh, yeah, I printed like the next array. Sorry that I'm being really weird. Okay, so this works on samples at least, but this should probably work for everything. Let's see. MLE, oh boy. I mean, I can, like, just actually reset the tree instead of remaking it, and that should be enough. That's kind of annoying, but okay. Okay, this should be enough. And then we just create it once, and then in every loop we reset it. And that should work, and use considerably less memory. Where is it? My white spacing is like very much not helping to make this clean. The statement changed. Let's check that out in a second. Maybe it just specifies like empty, non-empty, because that was like the one thing that wasn't clear. Okay, so this should actually work. Yep. How fast is it? Do I want to speed it up? It was okay. It's pretty fast, so we're all good. Let's speed the changes. Oh, so there was a typo here. Okay. Okay, now we just have to do the tree problem, which is not really something I want to do with this challenge, but what can? I mean, there's not much I can do about it. It just has to be done. How am I doing? Pretty okay. Okay, so for each K, count the number of... Oh wait, it's node labels. I see, I thought the edges had like weights or something. So... I think what we do is... Well, for like max being 0, we just have to count the number of paths that contain 0. So it's like if we remove the edges from 0, then we split into a bunch of components and we can count the number of paths in those components. So that gives us like the complement, we just subtract to get the zeros. So then the next one is 1, and we have to have 0 and 1. So what do we do? Oh god. I'll fix it. So if it contains 0 and 1, it also contains like everything in between. So I guess we kind of want to compress and then see the components that are left. And those are the ones that don't have both 0 and 1. So actually it might be better to start from having everything. Okay, so we actually like don't start at everything. We so we find the largest Okay, so I guess what we want to do is like find the largest I such that everything from 0 to I is on a path, and then after that if we start there, and then like everything that contains so we get like the two extremes of the path for each one. I think I'm no longer making any sense. Okay, let me think. Okay, I think we can do something to like count the number of paths with MEX at least something. And after that, we just like subtract. So what I believe we will end up doing is like we find like all the ones that are like on the same path, and then what are you saying? Okay, how do we do that first? How do we find like like the largest k such that 0 to k are all on the same path? That is what we need to solve first. I think after that it gets considerably easier. Question mark. So we root it at 0, then we do a DFS keeping like I'm not sure. How do we check if a set of vertices is collinear? I guess we just start at like the deepest vertex in each subtree of 0 and check that we hit everything on the way. And that should be enough. So do we want to like binary search that? I mean, I guess that's like easy enough to do. Oh, it's test cases too. That makes it a bit more annoying, but whatever. Yeah, so then after that, we'll get like 2 different lists of vertices, and we're just going to pop from each. Pop something from each. And yeah, kinda. Like every edge that is not in the path will get added like by default, and then we do some TSU merges. except we want to like delay those merges until like the extreme actually changes. Okay, this is not as fun to code as I would have hoped. It's probably doable though. Is there any way to simplify it a bit? So let me just run this for a case on paper. So for this case, which is like a star rooted at 0 with 3 other vertices, so at least 3 we have 1, at least 2 we have delete this, we have 3 times 1, 3, then delete the 1, at least 1 we have. Well, actually it works slightly differently when we just have one vertex, I think. Like you just take binomials of the sizes of the subtrees minus something. This is just 6, this is also 6, and thus we get 0, 3, 2 and 1, which is incorrect. So I think this idea should work. It's just not very fun to code, but I guess you gotta do what you gotta do. Oh, don't open anything. Okay, so what will we need? Okay, I'm going to stop speaking for a bit to try to focus. Okay, couldn't quite get that working. Let me see if I can just fix it quickly. Um, um, uh, I think this works. No, not quite, not really. What am I missing? Okay, so first of all, I wonder if that is computed incorrectly for some reason. Okay, I think that's like pretty scuffed, but whatever. I guess I can try to briefly explain the solutions, though I didn't plan this, so it's probably going to be really terrible. But we can like try, I guess. Yeah, I'm a bit disappointed that I didn't get that last problem, but it's okay, I guess. Did a bit better than expected anyways. Okay. This is from swap pass some time ago. Okay, so problem A, I guess. So you want the maximum k such that this happens. Okay, so what you do is you write n in binary. So let's say n is 13. Then its binary representation is the following. And what happens is if you take a look at the highest bit that is set, then when you look at the numbers smaller than n, so this is 12, this is 11, etc. The first few will all have the same bit set. So you have to go all the way to some number that doesn't have this same bit set. So this in this case is 7. And if you look at how this actually works, the number right after this one is one that has only this bit. So these two numbers on their own have and equal to 0, and that means that everything, if you include everything else up to n, that also has only and equals to 0. So the solution is just find the first number that doesn't have this bit set, which, if you want to write it in terms of math, really just reduces to finding the minimum number of this form, 2 to the m minus 1, that is smaller than n, and that's your answer. Problem B was hard. So you had a game, you have some bit string, and what you can do is you can choose some position and make it into a 1, and that costs you 1. Or you can take this entire string and reverse it. Which has cost 0. But you can only do this if the current string is not a palindrome. So, for example, this, you can't reverse it. And what else? And you can't reverse 2 times in a row because it would become like an infinite loop. So 2 players play their turns, and the game ends when everything is 1. And the question is, who pays less if they both play optimally? So the first subtask is the initial string is a palindrome. So what happens in this case will be dependent on whether the middle character is a 0. So what happens is, let's say either n is even, or the middle character is 1. Then what happens in this case is that Bob wins. And the reason this happens is if you look at a string where everything is 1 except for 2 positions that are palindromes, let's say that it is Alice's turn. Then she will have to choose to play on one of these ones. It doesn't matter which one. What you then do as Bob is reverse the string, and you force Alice to take the other one, and you win. So what you're going to do as Bob is, whenever Alice fills in a 0, you just fill a 0 in the opposite position to force it to stay as a palindrome until the last pair. And then in that case, you just do this and force Alice to take both and win. So when it is a 0, so let's say this string or something. Well, if it's the only 0, Alice just loses because she instantly has to take that 0. So in this case, Bob wins. In any other case, what you're going to do is take the middle as Alice. And then you're just going to use Bob's strategy. So in this case, Alice wins. So that's the only cases. If n is even, or the middle is 1, or the only 0 is right in the middle, Bob wins, otherwise Alice wins. So in B2, the initial string can be any string. And we've already solved for palindromes, so we just have to take care of the non-palindrome case. So the key observation is that if the initial string is not a palindrome, then Alice can never lose. So why is this? It's because if Bob had a winning strategy, then when Alice reverses on the first step, which she can do because the string is not a palindrome, Bob has some reply because he has a winning strategy, and then you can just play the reply originally. So you can steal Bob's winning strategy, so he can't ever have it. So then the only question is, when is this a draw? And the answer is, again, dependent on the middle character. Okay, this part is kind of annoying. So what you're going to do, let's assume middle is not 0. Well, it doesn't actually matter. What you're going to do, playing as Alice, is you're just going to repeatedly reverse. And you're going to look at the opposite pairs. So let's say you have a pair of zeros that is symmetric. So if Bob plays one of these zeros, what you're going to do is just do the same. And otherwise, if he plays somewhere else, the string is still not going to be a palindrome, or it's going to be, but okay, let's see. Once it's a palindrome, you just analyze it with the opposite, with this part, and see that Alice wins. So if you can play in the opposite position and also make it a 1, then you do that, unless it's like the last move, and in that case you reverse to win. And otherwise, the string is still not going to be a palindrome, so you're just going to reverse it and force Bob to play in all the bad positions. So you can think of 3 pairs of characters, symmetric characters. You have ones that match with ones that don't affect anything. You have zeros that match with zeros, which half of them are going to be taken by Alice and half of them are going to be taken by Bob. And in all the remaining pairs, and there is at least one of them, Bob is going to take all of these zeros. So the only weird thing is, again, the middle character. So it turns out that there are special cases. If you have the middle character as 0 and exactly 1 unmatched character somewhere else, so this pair is symmetric and they're different, then these cases are all draws, and you can check it very easily. whatever Alice does, if she reverses, Bob just makes it a palindrome and forces Alice to take the other. And if she takes, then Bob just takes the other. And it turns out that this is actually the only draw case. So in every other case, Alice's strategy is going to be basically this repeatedly reverse, and then eventually do this reversing thing to win the last pair of zeros. It's kind of annoying, tricky to analyze, but that's like the full case analysis of exactly what happens in every position. I probably didn't explain that well at all, but you can like try to play it yourself and figure out what these strategies mean, I guess. Okay, problem C. Let me copy the array from the example. So, problem C defines the cost of an array. Is it called the cost? It's called the weight. Okay, you define the weight of an array to be the number of pairs of equal elements. So this, for example, has weight 3. And what you want to know is the sum of the weights of all the subsegments. So what you're going to do is solve for each value independently. And our strategy, so let's say we're looking at 1, so we consider 1, we don't care what this position is, just it's not a 1. And the other ones. So what we're going to do in order to add up the contribution for all these ones is we're going to consider every pair, and we're going to count its contribution to the answer. So the question now is, how many subarrays contain this pair? So let's say this one is at position I and this one is at position J. Then the number of subarrays that contain both of these positions is going to be equal to, assuming 0 indexing, it's going to be I plus 1 times n minus j. So in fact, if we just fix the leftmost one, then we're going to have I plus 1 multiplied by, say these are j and k, or maybe like j1 and j2. Then we're going to want to multiply this by all the values for the right endpoints. So n minus j1 plus n minus j2 and so on, n minus j whatever. So after we switch to having this one as the leftmost, then we're just going to want n minus j2 and all the followings. We're going to want to erase this one. So what we actually do is pretty simple. We just store some suffix sum for this array of n minus j somethings. And that way we can answer what this product is in constant time. So that allows us to solve for each value in O of number of elements with that value. And then we just do that for each value and get a no event solution. Problem D, which was the one I didn't finish implementing. We have some tree. We're going to consider all the paths in this tree, starting at some node and ending at some other node. And for each of these paths, we're going to compute the MEX of all the values. In this case, 3. And what we want to output is an array of n+1 elements, which is how many paths have each possible MEX. So I think this was the sample, and the answer was 1 has MEX 0, this 2, 3 path, 2 have MEX 1, 1, 1, and 1. Okay, so what does it mean for a path to have MEX at least n? At least n. Well, at least k, let's say. So the condition for this is actually very simple. It's just that it contains all the numbers from zero to k-1. So what we're going to do is count for each k how many paths have at least k, and then we can know how many have exactly k by doing some subtraction. So we are looking for paths that contain 0, 1, 2 up to k-1. So in particular, they are in the same path. So the problem, of course, is that this is not always possible. So it actually was in the samples because they're both just path graphs. But if you consider, for example, this, a star with 4 vertices, then it's not possible to have all 4 vertices in the same path. So what we're first going to do is figure out what's the max possible value of k. And the way we do this is by binary searching. And the way we check if some number is possible is, let's say we're checking if it's possible for all of them to be collinear. We're going to root the tree at 0. And then what we're going to do is very simple. We take the deepest node among our first k, and then we walk to 0 and check if we hit everything by doing that 2 times. So let me draw like a more interesting example. Okay, this should be a bit better. So let's say we're trying to check if these red nodes can all be in the same path. This is always node 0, this topmost node. So what we're going to do is we're going to start at the deepest node and walk up to node 0. and then do the same one more time. Start at the deepest node that we haven't visited and go up. So in this case, we actually visited every node, so that means we can get them all on the same path. If we, for example, we're also trying to visit this, then our second step would be actually to start here, because this is the next deepest node we haven't visited. But then we can't visit this last node, so we just lose. Okay, so we figured out how to do this binary search step, and now we have the maximum k such that the nodes from 0 to k can be in the same path, and we also can get the endpoints of the path. So after that, what we're going to do is actually pretty simple. So let's say we have the endpoints of the path containing the first m vertices. So any path that contains all of them must also contain the entire path. So something like this. And then what we actually do to get the rest of the paths that contain this is very simple. We just start at one of the endpoints and just trace some other path starting at it. So for example, we can take this green path over here, and we can also do that for the other endpoint. Let's say there's another vertex here, then we can start here and walk to some other vertex, and that's also a valid path that contains all of these nodes. So what we actually need to know is just how large is this component of this endpoint, and we can keep that by using disjoint set union, union find structure. And after that, when we reduce m, so let's say we now want m minus 1 and this node stopped existing, then we just walk until we reach the next node in the path. So we'd expand our component to something like this. And yeah, that's basically the solution. And there's some special case maybe with 0, because 0 is going to be the endpoint both times, but it's pretty much the same. Okay. Finally, problem E. So basically you have some array. Let me just write the first part of this. So you're going to define the cost of this array as basically take every distinct element of the array, take its first position and take its last position, and the distance between those. Then add those up, and that's the cost of the array. So here it's going to be 0 from the 1, 0 from the 4, and 3 from the 6s. So what the problem actually asks you to do is you have some array, and you're going to divide it into some number of subarrays. The number is given. And you want to minimize the sum of the costs. So this is actually pretty straightforward. What we're going to do is compute some DP, and the state of the DP is going to be some suffix, and the number of segments. And then at the end, our answer is just going to be the DP of the entire array with k segments. So how do we actually compute this? Let's say we're looking at some suffix of the array. So the naive way is to just iterate over. We're going to look at the subarray containing the first element, and the naive way is to just iterate over all the possible endpoints. And you can like just compute the costs like linearly, it's not too difficult. So this will lead to a linear transition, and this is going to be O of n squared times k. So we want to make this faster. So what we actually want is something of the form maximum of the cost of some subarray, let's say from L to R, plus the DP of the suffix after that, and k minus 1. So this is our transition explicitly, and this is actually just a range maximum, assuming we can keep the costs updated. So if we can find a way to keep the costs updated, then we can just solve this by using a segment tree, and this will improve it to nk log n. So the way to update the cost is actually pretty simple. Let me just write some values or whatever. So let's say we're now looking at this suffix, and we just included this new element. Then we're going to find the next position where it appears. And what does it mean to include these three? It means that this this distance will now be counted in the answer for the threes. So what we actually have to do is pretty simple. Just we can keep the costs of of the arrays ending at each position. Then what we just do, what we do is we just add this new distance for all these positions, because all of these arrays will now include these extra 2 units. So we can pre-compute these jumps to the next position with the same element, and after that all we need is to add something in some suffix and range query maximums. So we can just do that pretty easily with a lazy segment tree. And that's the solution. And that's all the solutions now. I don't know if we passed or failed or something. Let me see. It seems like everything will just pass, which is nice. Okay, so that was this Codeforces Round 721 with this font. Okay, see you next time.